All right, folks, welcome back. We have moved into section 11.5. We're now looking at graphs of polar equations. If you recall, in section 11.4, we introduced what polar coordinates are and how you can convert between x comma y to r comma theta, where x comma y are rectangular coordinates and r comma theta are polar coordinates. So what we're going to look at now is how we can actually graph polar equations, and then we'll look at solving polar equations. The easy part of this is to graph them, because we're gonna rely on our graphing calculator for help with that. The more challenging part is to actually find solutions of where two polar graphs intersect, and we'll spend most of our time in section 11.5 working on those types of problems. So this notes page you picked up is really just a reference sheet. I give you the format of what circles look like in polar form, and you can see what those graphs look like and what the equations look like. And a new type of graph called a rose. Give you the generic form of those equations, and then 3 different examples for you to analyze. And then we have this third type of graph here, which I will be honest, I have no idea how to pronounce this word. It looks a lot like leprechaun to me, but that's probably incorrect. Those equations have this form right here, and this is a special case called a cardioid, which kind of looks heart-shaped. Okay, not so important that you know the names of these, or I'm not going to require you to memorize the different forms of those equations. You just need to be able to work with them. What I do need you to be able to do is graph these polar equations on your calculator. So let's do an example of that right now. So I'm going to go ahead and open up my TI Nspire CAS calculator. I'm going to show you how to do this on the TI Nspire. You're going to need to do this if you have a TI-84. Unfortunately, I can't show you how to do that in this video. I'm going to have to either create a separate one or just show you in class. But let's go ahead and do it here. I'm going to go ahead and open a graphs page. And let's say I want to graph how about 4 times the sine of 2 theta? Well, I can't do that here because this is a function in x, and I need an equation in theta. So let's go to Menu, Graph, Entry, Edit, and if you look, we have 8 different options here, and we spend most of our time in this function realm. But let's go down and look at option 5. On my calculator, option 5 is polar. If you don't have the most recent operating system, you could be at a different the polar option could be a different number for you. But what we're going to do is turn into polar mode for graphing, and it gives me the following: R1 of theta equals. Well, I mentioned the example. Let's do 4 times the sine of 2 theta. Okay, so I'm 4 times sine of 2 theta. I'm still in radian mode, which is important. And then take a look down here. This line right here tells us that theta is going to go from 0 to 6.28. And 6.28 should be a decimal that you recognize. It's approximately 2 pi. So theta is going to go from 0 to 2 pi, and it's going to step 0.13. So it's basically going to start at 0 and plot a point, and then it's going to go up it's going to increase theta by 0.13 and plot another point, and it's going to continue to do that until it gets up to 6.28. And when we grip it and rip it, we're going to get a graph that looks like this. Hey, that's great. That's kind of like what some of the graphs on our notes page looks like. The only other change I'm going to make here is I'm going to go Menu, Window Zoom. Let's pick a trig zoom that's custom built into the calculator, so it's kind of going to give us a better view of that graph. Let's say I want to graph another polar equation. Let's say this one's just going to be r equals 2. And you ought to think about that before I hit enter and say, well, if r equals 2, that means theta has no influence on what the graph looks like. It's just going to be a circle centered at the pole with a radius of 2. I grip it and rip it, and there's my circle. So this is actually going to be the first example of a system of polar equations that we solve. That's why I picked this one to graph for you. But if we take a look at these two graphs, we can see that they intersect at 1, 2, 3, 4, 5, 6, 7, 8 different locations. And again, this is how you're going to graph polar equations on your calculator if you have a TI Inspire. If you have an 84, it's going to be similar strategy, but I'm going to want to show that to you in class. On the 84, you're going to pick mode and then go switch from rectangular to polar, and then you're going to use the theta button, which is the same as the X button. And again, if you have an 84 or an 83, I can show you that in class. All right, let's move on. Page 2 of the notes shows us a procedure. Solving systems of polar equations, a simplified approach to what is presented in the textbook. This procedure will enable you to find the points of intersection of two polar graphs. On your notes page, I gave you a specific reference to some problems in WebAssign. I took that reference out here because it actually could change from year to year depending on what problems I pick. So I'll show you the example problems I give. I'll reference a problem number in WebAssign. Just know that this is a general procedure for finding the points of intersection of two polar graphs. Step 1, graph the system of equations and count the number of intersections. Make a sketch of the graphs and highlight the intersections. If the graphs intersect at the pole, which is what we used to call the origin, note that separately. This procedure will not produce the pole as a solution. So if we see in our graph that the two equations, the graphs of the two equations intersect at the pole, we have to note that separately. From this example right here, I graphed 4 sine 2 theta and 2. They do not intersect at the pole, so I would not need to note that separately. Step 2 is solve the system by setting the two equations equal to each other. Check to see, and I'm going to let you read through the bullets. I don't need to read through all those for you. But what's important to do here is go down to the third bullet here where it says, if you need to find additional solutions, proceed to step 3. So you only need step 3 if step 2 doesn't produce all of the solutions that you see in your graph. So if we're trying to find the solutions of, or the points of intersections of these two graphs, we count these out before there are 8 of them. And this is actually going to be our first example problem where we're going to test this procedure, and it's right here. Okay, we're about to solve systems of polar equations, and our first example is find the exact polar coordinates of the points of intersection of r equals 4 times the sine of 2 theta and r equals 2. Now this problem is similar to what you'll see in question number 13 in WebAssign. So I made that note for you here. And the first thing we're going to do is take a look at the graph. Again, we already graphed this. We kind of know what it looks like, but there's a graph that we can use throughout solving this system of equations. And step 1 says, if I go back to my procedure, step 1 says, graph the system, count the number of intersections. Okay, so we got the thing graphed. Let's go ahead and count the number of intersections. We have 1, 2, 3, 4, 5, 6, 7, 8. For step 1, we're going to write 8 intersections. And we're going to say none at the pole. So the pole is not a solution here because you look at the origin of the graph, or the pole, the two graphs don't intersect there. So we do not have a solution at the pole. Okay, now I'm going to go on to step 2 of the procedure. And step 2 says, solve the system by setting the two equations equal to each other. So I am going to set the first equation, 4 times the sine of 2 theta, equal to 2. I'm going to go ahead now and I'm going to sprint through the algebra required to solve this equation. Okay, so I've solved that equation, 4 sine 2 theta equals 2, and what I have are all of the exact solutions. I have pi over 12 plus pi plus 12 pi k over 12 and 5 pi plus 12 pi k over 12. And I really only need to list the solutions on the interval from 0 to 2 pi. So on the interval from 0 to 2 pi, theta is going to equal, and I'm going to list these in increasing order. So pi over 12 I get from this first theta, and then I'm going to get 5 pi over 12 from the second theta. Back to the first theta, I'm going to get 13 pi over 12. And to the second theta, I'm going to get 17 pi over 12. And that's it. If I continue and try to find the next increment of theta, I'm going to be above 2 pi, so I'm going to go ahead and stop there. So I'm now actually ready to list out the solutions to my system of equations. And those solutions will be, they will be in the form of r comma theta. So r comma theta, r, recall r is 2. So all this is important to note. All solutions of this system will have r equals 2. That's important to note. So let's go ahead and list our r comma theta pairs. We're going to have 2 comma pi over 12. And we're going to have 2 comma 5 pi over 12. We're going to have 2 comma 13 pi over 12. And then we're going to have 2 comma 17 pi over 12. And that's all of our solutions. And at this point, some of you should be concerned. You should be saying to yourself, hey, wait a minute, this is only 4 points. And that's a problem because we need 8. Why do we need 8? Go back and take a look at our graph. We counted 8 intersections there. If we need 8 intersections, we must go to step 3. And step 3 of the procedure, let's click back and take a look at that. Step 3 says, if you have one equation where theta is a free variable, such as r equals 7, solve the system again, but this time take the opposite of r. So let's take a look at our system. We do have r equals 2, so theta is a free variable, can be anything in that equation. So what we have to do, so moving on to step 3, we're going to have to solve the equation 4 sine of 2 theta equals -2. And I'm going to go ahead now and sprint through the algebra of solving this equation. Okay, so I've solved the equation 4 sine 2 theta equals -2. I found all exact solutions, 7 pi plus 12 pi k over 12 and 11 pi plus 12 pi k over 12. What I'm going to do now is list out the exact solutions on the interval from 0 to 2 pi. And I'm going to list them in increasing order from smallest theta to largest. This is going to give me theta equals 7 pi over 12. 11 pi over 12, 19 pi over 12, and 23 pi over 12. This turns into the following solutions in r comma theta form. Remember, our R value for all of these angles is -2. So we have -2, 7 pi over 12, -2, 11 pi over 12. -2, comma 19 pi over 12. And finally, -2, comma 23 pi over 12. And those are the final 4 solutions we needed. So these are the 4 additional solutions we needed. And that's exciting because we're done with this problem now. The one thing I would like to mention to you is that when you enter these answers into WebAssign, WebAssign asks for you to enter them from smallest R value to biggest R value, smallest theta value to biggest theta value. So you're going to enter these ones with all the negative R values first in increasing order of theta. So this would be your first one, second one, third one, and fourth one. And then you'll go back up and enter the positive R values. So this would be your fifth one, sixth one, seventh, and eighth. And again, negative theta first, then positive theta, or excuse me, negative R first, then positive R with increasing order of theta. Okay, folks, that's it for this example. I think you'll find the next example is quite a bit quicker than this one. So this one says find the exact polar coordinates of the points of intersection of r equals 3 cosine theta and r equals 1 plus cosine theta. This is very similar to WebAssign example number 14 or WebAssign problem number 14. First thing we're going to do, look at the 2 graphs. There's the system of equations graphed out, and let's go ahead and count intersections. So we have one intersection right here, one intersection right here, and then lo and behold we have an intersection right there at the pole. So step 1 of the procedure says count the number of intersections in the graph, and we're going to say 2 intersections plus pole. And in WebAssign, if the 2 graphs intersect at a pole, you're literally going to write the word pole as your final solution in your comma-separated list. Okay, so to solve this system, we're going to go to step 2 of the procedure, which says set the 2 equations equal and solve. So we have 3 cosine theta here. Is going to be equal to 1 plus cosine theta. Okay, so first step I'm going to do here is I'm going to subtract cosine theta from each side. That's going to give me 3 cosine theta minus cosine theta equals 1. And I'm specifically showing you this step, not sprinting through it, because I anticipate some of you might get stuck here. But it's really quite simple. Cosine theta is the same here and here. This one is 3 times cosine theta. If you have 3 of something and you subtract 1 of that same thing, you end up with just plain old 2 cosine theta. And we have 2 cosine theta equals 1, which means that cosine of theta equals 1/2. And we know that on the interval from 0 to 2 pi, theta is going to be equal to pi over 3 and 5 pi over 3. And some of you might be asking yourself right now, why didn't he put the plus 2 pi k thing in here? I'm so confused. Well, the reason why I didn't do that is because I had just plain theta in there. There was no multiplier or divisor in there that would give me multiple solutions on the interval from 0 to 2 pi. On the interval from 0 to 2 pi, I just have 2 solutions, pi over 3 and 5 pi over 3. So that makes this problem considerably easier than the previous one. So what do we do now? We have to find r. Okay, well, to find r, we're going to substitute theta into either the first or second equation. Doesn't matter which, because if these are solutions to the system, we should be able to substitute them into either one and get the same answer. So let's go ahead and we'll substitute the first one into 3 cosine theta and the second one into 1 plus cosine theta. Just for fun, we'll do one of each. So for R1, we're going to say that's 3 times the cosine of pi over 3. Well, the cosine of pi over 3 is 1/2, so that's 3 times 1/2, which is 3/2. And for R2, let's use the second equation, and for the second theta. Now, I don't think that you have to use the second equation here. You could use the first one as well. I'm just showing you that you can use either. So we're going to have 1 plus the cosine of 5 pi over 3. And that's going to be equal to 1 plus, let's see, the cosine of 5 pi over 3 is 1/2. 1 plus 1/2 gives us 3/2. All right, now we have an r value that goes with each theta. So this r value here goes with theta equals pi over 3. And this r value here goes with theta equals 5 pi over 3. They happen to be the same value, and that should make sense to you. Take a look at the picture. If you look at the picture, the distance from there to there, that r is the same as the distance from there to there. So that's why we ended up with the same r value for each solution. So our last step is to go ahead and list our solutions in r comma theta form. They will be 3/2 comma pi over 3. That's our first solution. 3/2 comma 5 pi over 3. But wait, there's 3 points of intersection. Why do I only have 2 solutions? Oh yeah, don't forget about the last one. They intersect at the pole. There's your solutions to this system of equations. Good luck in WebAssign, folks. I'm going to put together a couple more videos showing you some more crazy polar systems and how we can work at finding the points of intersection. One last quick comment here before I end, folks. I just want to make a note here. We found all 3 solutions. So, step number 3 of the procedure in your notes is not necessary. We didn't need it because step 1 and 2 gave us all the solutions to the system. All right, that's it for this video, folks.